let's go through a bit of this. It says the motion of a rocket is complex. A lot of problems we've dealt with so far have been involving constant force and constant acceleration. But like it says, the thrust force of a rocket is actually often not constant. And so we also find that the mass of the rocket may change as the fuel burns. And a lot of times so far we hadn't dealt with situations where masses were changing. It was just always a constant mass. And we also want to incorporate the past ideas of drag forces acting on the rocket as well. And so we'll begin by starting with a very simple model, and then we'll build it up to more and more complicated calculations. Alright, so first thing we have to have some data. So let me show you what the file looks like here. As you can see, it's got a column for time, and it has a column for the thrust, the rocket thrust. And that's in newtons. So this is a force that's being provided, like an upward force, due to the engine. Alright, so let's see. You're going to have a rocket mass. Yeah, in the lab it says you'll model the flight of a 230 gram model rocket, but it carries initially 25 grams of fuel, so that gives us actually a total of 255 grams. So when you fill this file out, you want to put 0.230 for the rocket mass. 0.025 kilograms for the fuel. Add those together and you get 0.255, yeah. The first thing to do is to find what's called the impulse. It says here in the lab that to find the total impulse, we actually want to add up all the multiplications of force times delta t. And let's just look at what this graph looks like. Alright, so you can just select your columns. And this would be a good thing to do, is just go to Insert and look at a scatter plot of it. Okay, that's what it looks like. So this is clearly not a constant force. As time goes on, the force just starts off at 0. It ramps up to a peak, and then the force just kind of decreases steadily from there, eventually dropping off to nothing, so all the fuel's burned at that point. Now we're going to have another column here for the impulse. And, what is impulse? Well, let me share this graph and I'll draw on it for a minute. This is a graph of a force being applied versus time. And when we find an impulse, what we're doing is we're multiplying the force times time. So we actually want an integration of all this area under the curve. Get the area under the curve, is called the impulse. It has a letter J, and that stands for impulse. Alright, so we just want to go from some initial time to some final time. But this is going to be a discrete kind of calculation. Alright, so the units will be, of course, newtons times seconds. That'll be the units of impulse. There's a lot of things you can do with impulse when it comes to collisions and things like that. So let's calculate it. To calculate it, we'll just take each force value and then multiply it times the delta t. So column B15 here times 0.04, because that's the incremental step of the time. So the next one would be B16 times 0.04. B17 times 0.04. So it's a force times the time. Alright, now it's not showing the digits. If you just click Format, Cells, and then change the number of decimal places. Alright, and drag that down. You can't really see all the decimal places unless you do that. Now I can see much more. Alright, there we go. Now that I have all these little impulse pieces, I want to add them all up. So at the bottom of the column, I can do a sum. So type equals, and then sum, and we can go from C14 to C58. So you type in C14, then colon, C58. That's going to sum up all your impulses. Looks like we get 20, but I think I want to show more digits on that. Okay. That's going to be my integral approximation. So that is the impulse for the whole thing, for the entire 1.76 seconds. I went from t equals 0 to t equals 1.76 seconds of the force dt. So that's actually this part right here. Alright, now what the lab is saying though is that you could find an average force if you take your integration and then divide by the time interval. It's like a weighted average type of thing. But what you're finding is you're finding an average value of this graph. So if you take and divide by the delta t of 1.76, then you get what's called the average value of the graph. So let's find out what that is. Now we can just take our result from above C61 divide by our time of 1.76. Okay, 11.4. Let me show some more digits though. 11.3727. Alright, so what's the meaning of that? If we go to our vertical axis and find 11.3, which might be right around there, we could do a dashed line here, which represents the average value. That's if you just find the middle of all the force values. It would be called FBar, it's called. So why would we do that? Well, interestingly, the results that we get from the actual curve and the results that we get from just using the average value in some calculations can be similar. So if we take the area under the FBar curve and add that up, the impulse would be the same from 0 to 1.76. That's what they're saying right here in the lab, is that the integral of the actual curve on the left will equal the integral of FBar dt using those same limits. And so they're saying since FBar is constant now, you could pull it out front. And just do this, which is basically like just doing FBar times delta t. And that would be represented by the area under that curve. Alright, so let's see how things work out. Now if we make a new column for FBar. Now it says here that you want a value between 11 and 12, so it tells you what to look for, which is what we got. And it wants us to find the maximum height by hand and compare it to what we get from the spreadsheet. Alright, so let's do it by hand first before we make the rest of the spreadsheet. They talk about event 1, event 2, and event 3. So event 1 I would call like basically the start. And then event 2 would be when you run out of fuel. That would be a time when there's a major change in the problem. And event 3 could be reaching the peak. Now obviously we're going to start at time 0. We're going to start at a position of 0 and a velocity of 0 as well. Now, as far as the acceleration goes though, let's find that. Because what's going to happen is we're going to pretend like we have a constant force. For 1.76 seconds. And then we want to find out if that was the situation, what would the acceleration of the rocket be like? And it would be constant for a while until you run out of fuel. And then what would it drop down to? Well, it would drop down to negative 9.8, free fall. And then you'd maintain that until get to the peak. So it's a piecewise kind of situation. So we know that T2 is 1.76 seconds. That's when the major change happens. So that's what you want to put here. You run out of fuel at 1.76 seconds. And the acceleration of this second part is going to definitely be negative 9.8 because we'll be in free fall. Now, what happens to the force? Well, the thing is that the force is not going to actually become zero, because when we do motion problems, we really care about the net force. So the force is actually going to drop down to a negative value as well. And so that begs the question of, what really is the net force? Is it that 11.37 that we found? Or no? The answer is no. That was a force of thrust, but it's only one force on the rocket, see? So there's an upward force, which we'll call like FBar, but there's also a weight to the rocket, which could be called FG or W. Alright, so we'll treat the thing as being 255 grams. So when we calculate our weight, we want mg. So let's just do W equals 0.255 kilograms times G. 2.499 newtons. Okay, and then our F bar was from the spreadsheet 11.37. Alright, so we want to find now the net. The net is going to be 11.37 minus 2.5. 8.87. Okay. Now let's find the acceleration. For that, we'll use Newton's second law. So we got to do 8.87 over 0.255 I'm getting 34.8 meters per second squared for that acceleration. And so that's what I want to put here. Alright, great. And then it drops down to negative 9.8. So what's the velocity going to do? That's going to be our antiderivative of the graph below. So we got a nice constant acceleration according to our model so far. We're not taking into account how the force changes. So we'll have a nice sloped up velocity. And then what's going to happen here for negative 9.8? Now we got a negative slope. So we'll go down to 0. It's a little out of scale though. And this is where the peak will happen. So notice that we'll actually reach our fastest velocity when the fuel stops burning. Okay, so this will be the time when we're moving fastest. Alright, and then we have a position graph. What we'll see for that is a curve where it reaches its highest slope right here, and then it's just going to kind of level off to a peak. That's when we reach our highest point. And in this page they're calling that R, which is basically like the Y value of it. Alright, so let's calculate how fast do we end up going at that fastest speed. We're going to want an integral of a dt from 0 to 1.76 because that's when the upward thrust stops. So we'll do an integral from 0 to 1.76 of the 34.8 dt. See, that's just going to be 34.8 times 1.76. Looks like we'll reach a top speed of 61.2 meters per second. So that's what you'd actually put here. Alright. We want to figure out how high do we end up going at this point. Like, what's the point of release, basically? They're calling that R2. It's this height here. Alright, so R2 could be thought of as an integral of the velocity graph. So we'll have an integral of 34.8 t dt. That would be the velocity curve. So 34.8 t squared over 2 from 0 to 1.76. Okay, so that'll be, I'm getting 53.9 for that. Alright, and then we want to find how long does it take to get to that peak. Okay, so we know the initial speed we're going. We're going 61.2. We know how high we are off the ground. So it's like, can we figure out how much longer it takes to reach that peak? So, using a motion formula, I might go with VIY plus AYT equals VFY. It's a formula we had used before. You know you want the final to be 0. You know the initial is 61.2. We will now be in free fall, so we want negative 9.8. And then we could use that to solve for the time that it takes to get to that peak. I'm getting 6.24 seconds more to get to the peak. Alright, so let's figure out how much farther that is in the y dimension. So y final equals 1/2 at squared plus vit plus y initial. So 1/2 negative 9.8 6.24 seconds. Initial speed of 61.2 at the release. And we'll do 6.24 seconds. And I said we were located at 53.9 meters when the release occurred. So what I'm talking about there is, just to be clear, there's a point where our curve changes from concave up to concave down. And I'm saying that if this is the release, then that happens at 53.9 meters above ground. And I'm trying to find y final, which is the highest point. And I said that the speed upon release was 61.2 meters per second. And I knew that this delta t here for my interval between release and peak was 6.24 seconds. So this calculation should give me that y final height. Let's see. I'm getting that the displacement between release and peak would be 191. And so if we add that to the initial position, I'm getting a total of 244.7. So 244.7 meters for the peak. Alright, that was a lot of motion formulas to use. And if I did it all right, then I want my spreadsheet to tell the same story. So let's go to the spreadsheet now and see if we can model this same situation. Alright, well, let's try it on the spreadsheet then. So to do the spreadsheet, you want a new column. And we'll call this first column just like a constant force or average thrust. And what you want to put in that column is just what you found here, 11.3727. And pretend like that was the upward thrust the whole time. So you drag it down. You may want to copy your time column over for each of these trials. You don't have to do that, but if you want, you could just copy A14, A15, then you'll have them right next to each other. Alright, now the average thrust doesn't tell the whole story though, because there's also a weight to the rocket. So for that we want the 0.255. So we basically want the sum of B6. So $6 plus $7. That's the sum of the mass of the fuel and the rocket itself. And then multiply by G. It's up to you if you want to put a negative in there or not. I'm just doing the magnitude of it. So it's going to be the same weight the whole way through. Then you can find the net force on the rocket. So that's going to be J14 minus K14 for me. Just a subtraction of the upward thrust minus the weight. Alright, so far I believe this is matching what we found by hand. Now we want to find the acceleration of the rocket. So net force divided by the mass. So far so good, right? That matches what we had found. But now we want to allow our spreadsheet to do a piecewise type of calculation. See, the thing is that after 1.76 seconds, the problem doesn't stop. It keeps going. We have to add that here though too. So drag your time column down. And I said that it would be like 6 seconds beyond the 1.76, so we want to go like quite a ways. Okay. And I'll drag this down as well. Alright, so our thrust though is going to drop to 0 after 1.76, so you just put zeros there, or just leave them blank. That's when the fuel stops burning. And there's a change in the motion. But our weight would still be there though. So you want to keep that going. Now I still want to calculate the net force. But as you can see, there's a sharp change from when the thrust is there to when it isn't. The net force goes negative, meaning it's being pulled downward toward Earth. And that'll affect the acceleration too, because now the acceleration is going to become negative 9.8. And we're in free fall now. Our next variable would be our velocity. And now we want to do the same kind of incremental addition that we had done previously in the last lab. So you start with 0 because we're at rest on the ground before the rocket, gets going. Then what we want to do is start with the velocity we had previously, so n14 plus an acceleration times a time. So I'm going to go with the previous acceleration, which would be m14 times the delta t of 0.04. Okay, in my next cell, I'll use the previous velocity, which would be n15 plus the acceleration m15 times delta t. And you just keep doing that so we can drag it down. And it shows how the velocity builds up with time. Let's see how high it reaches, see if our calculations were correct. Okay. It's coming up to around 61, 62. And yeah, we had said that velocity upon release would be 61.2 meters per second. So that's good. Alright, now we want to keep the calculation going of the velocity. See how it changes after that. It's going down now. It's going down because the Earth is pulling the rocket downward. So just keep dragging that down until you get to a special point, which is when the velocity reaches 0. Because when the velocity reaches 0, you're at the peak. Alright, right about here. This is the closest one. Okay, so we believe we're at the peak there. This is another important point. This would be the release. Into free fall. Okay, cool. Now let's do the position. So start off on the ground. Take your previous position, which would be 014, and then add your velocity times your time. So your previous velocity, n14 times delta t, gives you 0 at first. It takes a little while to catch up. Okay, so we're going up higher and higher. And then look at that. We reach around 53 meters. Okay, then we keep going upward. And we just want to see how high does our rocket go. We're looking for hopefully, I think 240 something. Okay, we're getting up to 256. I had said 244. There can be some lag with the spreadsheet where it doesn't perfectly predict it, because our delta t is not infinitely small. Yeah, alright, so it looks like the difference could be just due to like the lag in the spreadsheet, perhaps. One way to check it would be to make like a smaller delta t, I suppose. Just out of curiosity. It would be interesting to just change the delta t. See if we get results that are closer to the theoretical, you know? 'Cause it really wouldn't take much to do. You have to adjust this though. So instead of 0.04, I'm going to go 0.01. We'll count by 1/100th of a second. That would mean taking our, let's see, our velocity and just changing the delta t to 0.01. And then you want to do that for the position as well. And just drag that down. And this we'd have to keep going all the way to 1.76. And there we see that the release velocity is matching what we had said. So 61.24. If you compare that to what we had before, it's actually the same. Not surprisingly, because the force was constant. Let's see, 53 was our release position. So now let's go with this all the way to the peak. Oh wow, look at that. Here's our new peak, 248. So I guess the calculations weren't off, you know? It's just that there's a lag in the spreadsheet because of the large delta t. Alright, cool, good to know. So what do we want to do next? You know what would be cool before we even start the next one is to make graphs of what we had. So we could do this. Make a scatter plot. I'd rather get the net force though. Time and net force. It's constant for a while, but then there's a sudden change. Alright. Okay, that's our force graph. Move that over here. Now let's get an acceleration graph. Force and acceleration have the same shape. You can stack them one on top of the other. Then we'd like a velocity graph to see what that looks like. Okay, it heads upward until we get to the peak velocity. Then it starts to go down towards zero. Then we want a position graph. And it doesn't tell you to make these in the lab, but it's interesting to see. Okay, cool. We're accelerating. We're heading toward our steepest slope. Then we want to see a change in the concavity. Cool. That's our position. And it reaches about 240 to 250 meters. Alright, great. Now let's do it with the real thrust. So what we want to do is change this back to just thrust. And then we can copy the values from column B. Alright, for this we want column A. Okay. Gotta adjust some of these columns. Alright, it's changing our net force for us. Now let's get our acceleration. Start off with negative 9.8, but that acceleration changes quite a lot. Alright, cool. Now, let's see what happened. Interestingly, our release is still similar to what it was before. And that's expected. And then you want to see how high it goes. Okay, so right here, this is our peak. 253, 254, so really similar to what we had here. Alright, we can graph it though. Okay, there's our new acceleration. It's a variable acceleration. Alright. Let's get a new velocity. Okay, cool. New position. Alright, so fairly similar motions. That's what we want to see. But one's constant force and one's variable acceleration. The next thing to do, as the lab says, is to incorporate a changing mass. Let's see what they say about that. Part 4, variable thrust, variable mass. It says the mass of the rocket is not actually going to be constant. So we want to take that into account when we model it. At liftoff, it contains 25 grams of propellant that's not present once that thrust drops to 0. And further complicating the analysis is that since the thrust is not constant, the rate at which the rocket's mass decreases isn't constant either. So what they're saying is you can't just make a graph of mass versus time and say that it decreases linearly. And we now want to insert a column into our spreadsheet showing the mass of the rocket. Now the tricky part is how to make the mass change. So let's just set it up here for a second. I'll just copy all this. Well, yeah, so what I'm going to do is right here I'll insert a mass column. Now we know we want it to start off at 0.255, and then when we get to 1.76, we want it to go toward 0.230. And we need some kind of function that makes it do that. Then we'll calculate the weight based on the mass. So we'll just do column AU14 here. And just copy that down. After that, it can remain 0.23 for the rest of the time. Okay, nice. Now, how do we get the mass to change? Oh, they say it's a good guess to make the rate of mass loss greatest when the thrust is greatest, because the rate of fuel consumption would be greatest at that time. So if we assume that the rate of mass loss is proportional to the thrust, then we can set up this ratio where we have total mass lost over the total impulse equals the mass lost in each step over the impulse for each step. If you take this proportion that they gave you here, you could rewrite it by multiplying this part to the other side. If you did that, you'd find that the mass lost in each step, which is like a delta M, over the impulse in each step would be delta J. That could be set equal to the total mass lost over the total impulse, which would be just J. So multiply delta J to the other side, and you get that delta M equals the mass lost divided by the impulse times delta J. I'm going to make a new column. Mass lost at each step. I'll make another column for total mass lost. And this could be like a remaining mass column. Now they said the mass lost each step would be the delta M. And they're saying that it should be proportional to the impulse. So I think what I would do is I'd say we want to lose a total of 25 grams. Okay, that's how much we want to lose. So I believe that I would multiply that by a proportion of the impulse in that row, which would be C14, and then divide by the total impulse. You need 20.016. 0.025 times C14 over 20.016. Alright, copy that down. Alright, that's our delta M. Now to get our total mass, we just add that column up. So AV14 plus AU15. Here we'll do AV15 plus AU16 and just keep going like that. And perfect, look at that. It comes up to a total mass lost of 25 grams, which is what we want. To get the remaining mass, we'll do 0.255 minus AV14. And hopefully this thing's going to count down to 0.23. Perfect. Alright, so now it's calculating the weight based on 255 grams at the start, and it's calculating the weight based on 230 grams at the end, and that's what you want. Alright, so now we just have to adjust these columns so that they calculate correctly. When we calculate the net force, we want to do, let's see, we want to do our thrust AT minus the weight, so that column is actually good. For acceleration though, we want to divide by our remaining mass column. There we go. Alright, looks like our velocity column's already working as normal. And position as well. So here is our release point. Notice we're reaching 65 meters per second instead of 62, I believe it was, 61, 62, yeah. So we're reaching a higher speed because the mass is less. And let's see what our peak ends up being now. Okay, wow. We get a higher peak. 284 meters. Very cool. The last part is to just incorporate drag. And we want to use the formula negative BV times absolute value of V. Now the coefficient of drag, let's see. Well, what we'll use is 0.0003. Alright, so just fill in 0.0003. G is 9.8 times step is 0.04. Alright, so copy everything. I think everything looks good, so now let's incorporate drag. So to incorporate drag, we have to, if you remember from before, you have to create a column for the drag force. I'll put that right here next to the net force. The formula was negative B times V times absolute value of V. Alright, so we have to let our drag force reference the velocity column. So we'll start off with 0 drag because we're not going anywhere yet. No speed at the beginning. And then let's just do negative $B 8. That is our drag coefficient from the left side of the spreadsheet. And then we'll multiply by our velocity, which is going to be BN 15. And then we have to do times the absolute value of BN 15. And that should give us our drag force. Alright, so now we have to take our drag force into account though when we do our net force. So the net force should be that we want to add in BK 15. So now we take into account the drag force. Should be able to just copy these down. Alright, that looks pretty good because we're doing our drag force by using the velocity column, and then for our net force we have to use the drag as well. Yeah, so we'll get that. Let's change the number of digits that it shows though. Okay, we'll do that. As you can see, the drag force is getting to be a larger and larger size as the velocity is increasing, so that's a good sign. gets to its largest value here when the velocity is at its highest point. And then we'll just keep dragging that down. Alright, this is looking good. Drag those down. We hope that our drag force will go to 0 when we approach the peak. And we want our acceleration to approach negative 9.8 at the peak. Okay. And then another way to check it too is we want to reach a terminal velocity as we go forward. But it's going to take a while for that to happen. Yeah, copy all this. Our acceleration should go to 0 when we approach terminal velocity. Yeah, this is looking pretty good. Looks like a terminal velocity would be negative 86. The acceleration goes to 0. And the net force goes to 0 as well. Okay, cool. So the last thing to do is just to find the new peak. Looks like our new peak happens right here. 221 meters. So you could obviously do a graph of that. See what our new flight looks like with drag included. Alright, there's our new flight. It's starting to reach a terminal velocity here below ground. There's our new velocity curve. We reach that highest velocity at the release. We go to the peak, and then we're just starting to level off at a terminal negative velocity. So it incorporates drag as well. Very cool. There's our acceleration. Yep, we go at the highest acceleration. We release the thing. We're going into free fall, but it's not totally free fall because you got drag. And that acceleration should head towards 0 as time goes on.